So time to talk about the isotherms, the adsorption isotherms. But before that, we need to talk about the symbols and units we're going to use. And please note that the adsorbate is the substance adsorbed on the solid adsorbent. Okay, we talk about the concentration of the adsorbate in the liquid, or gas, if that's the case. I will say liquid from now on, but please note that you could have adsorption in gases as well. Okay, so C is the concentration of the adsorbate in liquid, and Ca is then the concentration of component A, either in gram per liter or mole per liter or something similar, depending on what's convenient. Q is the concentration of the adsorbed adsorbate on the surface, that is on the adsorbent. Qa is then the amount of substance A divided with the amount of adsorbent, and then you get gram A per gram adsorbent, or mole A per gram adsorbent, or gram A per kilogram of adsorbent, or some unit like that. We will always use equilibrium adsorption isotherms in this course. We will not deal with the kinetic stuff that you can do in advanced courses. So we will say that Q at equilibrium is a function of C somehow. And there are different isotherms: linear, Langmuir, Freundlich, and many, many others. Now, how can an isotherm look like? And I should say, isotherm, that means the same temperature. So isotherm is only valid at a certain temperature. And that you can actually use to change things. One thing that will be important in this course is to distinguish between favorable and non-favorable isotherms. So what is that? In Swedish, gynnsam isotherm. Well, the relation Q as a function of C can look in different ways. So here are some different examples. And the one up here, that's an irreversible thing. You just get it to stick, and then nothing more happens. Doesn't matter which concentration you have, essentially, you just get there. And yeah, so this is rather uninteresting in many cases. If you can't do it like this, that you mix the adsorbent and the liquid you have, you get the thing to adsorb, and then later you change the conditions, so this isotherm is not valid anymore. Okay, but we're interested in what a favorable isotherm is when we have some so the relation between the concentration and Q. So we're not really interested in this one here. So if the isotherm is such that you get high Q values for rather low concentrations, and then it levels off, then this is a favorable isotherm. You could say that you get unproportionally much adsorbed at low concentration compared to high concentrations. You have the linear here in the middle, so just straight on, QA equals K times CA. And then down here you have unfavorable ones. So at low concentrations, nothing much happens. And that's not what we want to have, because we want to take as much as possible away from the solution. So we want a lot to happen at low concentrations. So let's look at the Langmuir isotherm. I'm sorry for the Swedish here. This is increasing. This is ökande, is increasing in English. You have an equation like this. Q equals Q max times the concentration divided with a constant plus the concentration. Kd here is the dissociation constant. And if you take the inverse of the dissociation constant, you get the association constant. And here you see the interpretation of Kd. KD is the concentration at which you reach 50% of the maximum adsorption capacity. So 50% of the Q max here. And if you increase KD, then this 50% happens at a high concentration, which is not surprising thinking of this equation here, because at the concentration where C equals KD, then this term here, C divided by KD plus C, becomes 1/2. So high Ka means that it binds in well, while a low Kd means that it binds in well, right? Because Ka equals 1 divided by Kd. Another isotherm we will use in this course is the Freundlich isotherm. And it's K equals Kc to the power of n. And then you can have different numbers of n. And, well, if n equals 1, then you have a linear isotherm. And this is an empirical function with constants k then and n. And it's favorable if n less than 1, right? Because then a lot happens at low concentrations, and then nothing much happens. Now, this isotherm never saturates. There is no Q max here. Is this really reasonable? Well, depends. I mean, if you have a situation where you are far from saturation, perhaps a Freundlich isotherm is what best fits your experimental data, instead of this Langmuir isotherm, where you reach a plateau and nothing much happens. And you can compare with this with if you go to the cinema, there are a certain number of seats. So if there are 100 seats, you can get 100 people in there, and then in many countries they don't allow any more people to enter. You have a maximum. So a Langmuir isotherm is relevant if you have a single layer adsorption, for example. Then you reach a maximum level, and once you have reached that level, nothing more happens because all the sites are occupied. The Freundlich isotherm, you could say, might be suitable if you have a situation where you can bind in several layers. Then you don't have such a unique maximum level. And how do you know which one to use? Well, you have to fit isotherms to your experimental data and see what fits best. Now, the best option, I would say, is to least square fit to your data. So you take experimental data that are relevant for the experiment that you're going to do, so in the same range as your experiments, and then you fit your data directly to the isotherm as it is. An option is to first linearize your isotherm, so you get an equation y equals kx plus m. So for Freundlich, you can take the logarithm. When you do that, you get a linear equation. So log q equals log k plus n log c. So this is the kx term here, and this is the m, right? And for Langmuir, you can take the inverse, and then you also get a linear equation. But beware, if you fill around with equations like this and fit your experimental data, you don't get the same fit. You don't get the same parameters as if you take your original equation and fit it directly. It might not change that much, but it actually can change, and it can be important.